Hi guys, welcome back. Today we'll be looking at the gradients and the directional vectors. So let's start with the gradient vector. Suppose you have a function f, then the gradient vector of f in 2D is defined as the partial derivative of f with respect to x and the partial derivative of f with respect to y. And that of the 3D is defined likewise. So that will be the partial derivative of f with respect to x, f with respect to y, and f with respect to z. Suppose we want to climb this hill. Now the gradient vector will point to the direction when which taken will get us to the top of the hill more quickly. So that's it points to the direction of the steepest ascent. So that's the main idea behind the gradient vector. Now let's try some examples on finding the gradient vector. So with our first example, we are being given the function f of x, y, z, and we are being asked to compute the gradient vector. The gradient vector of f is defined to be the partial derivative of f with respect to x, the partial of f with respect to y, and f with respect to z. In computing the partial derivative of f with respect to x, we are going to treat all variables other than x as constants. So we are going to have eyz plus 0 because the last term has no x in it, so that will go to 0. Now let's compute the partial derivative of f with respect to y. So that we are going to hold all variables other than y as constants. So we are going to have xz eyz. We have xz eyz because this is an exponential function, right? So now we differentiate and multiply. So here when we differentiate yz with respect to y, we are going to have z. So then we multiply by x. That's why we have xz. Then plus 2yz. So we now compute that of the partial of f with respect to z. So that's going to give us xy eyz plus y squared. So then we write these guys in a form of a vector. So our answer is going to be the vector eyz, then xz eyz plus 2yz, then xy eyz plus y squared. So this is our gradient vector. Let's try our second example on finding the gradient vector. So here we are being given a function f and we are being asked to compute the gradient of f. So now computing the partial derivatives gives f of x will be given as 6x minus 2y, f of y will be given as minus 2x, and f of z will be given as 8z. So the gradient vector is given as 6x minus 2y minus 2x and 8z. So this is our gradient vector for the given function. We now move on to directional derivatives. The directional derivative of a function f in the direction of a unit vector u is defined as, for the 2D case, is the partial derivative of f with respect to x times the x component in the unit vector plus the partial of f with respect to y times the y component of the unit vector. For the 3D case, it's just the same idea. So the partial of f with respect to x times the x component plus the partial of f with respect to y times the y component plus the partial of f with respect to z times the z component of the unit vector. Also, we could be asked to evaluate the directional derivative at a point. So for the 2D case, the points will be x0 and y0. So we just have to substitute in these points into our directional derivative function. So that will be f of x0, then f of y0. So same for the 3D case. Also, we can express the directional derivative as a dot product between the gradient vector and the unit vector. Finding the direction derivative, you should keep in mind that the vector u should be a unit vector. If u is not a unit vector, then we have to convert u into a unit vector, and then we can move on to solve our question. So with this in mind, let's start solving some examples. With our first example, we are being given this function, and we are being asked to compute the direction derivative at the point 3, 4 in the direction of u. So here we should verify if u is a unit vector. So to solve this question, we need to verify if u is a unit vector. If u is not a unit vector, then we have to convert it to a unit vector before we can now solve this question. So cosine of pi over 4 is square root of 2 on 2, and that of sine of pi on 4 is square root of 2 on 2. So now let's compute the magnitude of u to see if it's a unit vector. So the norm of u will be giving us the square root, then we square the entry, so that will be 2 on 4 plus 2 on 4, which is 4 on 4, and that's 1. So here we know that u is a unit vector. So we can now move on to solve our question. So here we need to find the partial of f with respect to x and partial of f with respect to y. So we are going to have partial of f with respect to x being given as minus 4x, and partial of f with respect to y given as minus 1/2 2 times y, and that's minus y. So therefore the directional derivative d of u f of xy is defined as the gradient vector dots of the unit vector. So here will be u1, u2, and we have the gradient vector as minus 4x minus y, and we have our unit vector to be root of 2 on 2, root of 2 on 2. So here the x component here will multiply the x component here, and y component will multiply the y component here. So we are going to have minus 2 root of 2x minus root of 2y on 2. Now we were being told to evaluate this at the point p of 3, 4. So this implies that x naught is equal to 3 and y naught is equal to 4. So this will give us d of u f of 3, 4 is now equal to minus 2 root of 2, x is now 3, minus root of 2 on 2, y is now 4. So you're going to have minus 6 root of 2 minus 2 root of 2, and that's going to give us minus 8 root of 2. With our last example, we are being asked to find the directional derivative with the function giving us f of xyz in the direction of the vector v, which is minus 1, 0, and 3. So the first step is to verify if v is a unit vector. If v is not a unit vector, then we have to convert it to a unit vector. Now we ask ourselves, is v a unit vector? So now let's compute the norm to see if the norm is equal to 1. So we are going to have the square root of minus 1 squared is 1, 0 squared is 0, and 3 squared is 9. So that's going to give us square root of 10. So v is not a unit vector. So now we have to convert v to a unit vector. So to convert a vector to a unit vector, we just have to divide the vector by its magnitude. So we are going to have the unit vector, say u, is equal to minus 1, 0, 3 divided by the magnitude, that's root of 10. So we are going to have 1 on root of 10 then minus 1, 0, 3. So this is now our unit vector. So we use this guy to solve the given question. Now let's compute the partial of f with respect to x. That's going to give us 2xz minus yz. Then f of y is going to give us 3y squared z squared minus xz. Then that of f of z is going to give us x squared plus 2y cubed z minus xy. And also we have our unit vector to be 1 root of 10 minus 1, 0, 3. So we have our gradient vector defined below. That's f of x, f of y, and f of z. So now we move on to compute the directional derivative. The directional derivative is defined to be the dot product between the gradient vector and the unit vector. So we are going to have this guy. So we now compute the dot product between the gradient vector and the unit vector. So we can factorize 1 over root of 10 out. Then the x component will multiply the x component. So that's going to give us minus 2xz plus yz. Now the y component in the unit vector is 0. So that part will go to 0 plus 3x squared plus 6y cubed z minus 3xy. So our answer will be giving us minus 2xz plus yz plus 3x squared plus 6y cubed z minus 3xy. So here we don't have like terms, so we cannot simplify further. So that's our directional derivative. Thank you for watching. See you in the next video. Bye.